All right, so welcome back, everyone. I am Pedro Cenci Dal Castel. I am James' student, and this is Introduction to Cellular Potts Model lecture. So the idea of this lecture is to prepare you for the upcoming exercises and lectures where we are going to use CompuCell3D, which implements a Cellular Potts Model, and we will observe a lot of artifacts and unexpected things to understand why these can emerge and to understand how to control our cells and give them the behavior we expect. We have to understand, have a very superficial level of understanding of how Cellular Potts model works. So, and in this lecture, we'll focus on two main plugins: the volume plugin that controls cell size and the contact plugin that controls the cell shape. With those two, we can already build a cell that is roughly round and preserves its volume and preserves its shape. That's the simplest possible Cellular Potts model you can have. And of course, in the other lectures, we'll add more and more plugins. To start with, let's talk about Cellular Potts model in terms of where it sits among other methodologies. So when we're representing cells on a computer, there is a big variety of ways we can do so. For example, the cellular automata, one of the simplest ones, you define a grid, a lattice, and each pixel of the lattice represents a cell. Cellular Potts model, it's also in a lattice, so it is like a child of cellular automata in a way. Historically, that's not true, but you can think of it that way because both are in a lattice. In cellular automata, you have these pixels, and you can't really have your cells change shape. They are always a square, or if you are in a hexagonal square grid, they are always hexagons. And also Newtonian mechanics does not apply, so you don't have things like momentum or conservation of momentum or mass. You can still do impactful research using cellular automata, of course. This is one of the classic examples by Catherine Boltzmann. Yes, we are screen sharing. Am I not screen sharing?
No, you are. Kyle, maybe check the top bar of your Zoom. You might have accidentally clicked over to
All right.
the wrong tab.
All right. Okay, let's keep going.
Yeah.
So in this famous example here, each cell, again, is a pixel. The color is representing the state of the cell. The cell can be infected, can be healthy, or can be dead. And you can use that to model infection spread. You don't really care about cells moving, so it's fine to use something like cellular automata. And you also can have cells moving in cellular automata. We'll talk about that later. Another way you can represent cells is using center model approaches, where each cell is a point particle. This is a very simplified approach, but you gain a lot on speed because you can have many more cells. When your cells are simple in your simulation, you can have more of them for the same performance expense. This is a lattice-free representation. You do not have a lattice. Of course, you have the spatial resolution, but that's something you can adjust sometimes without even changing the behavior of your simulation. The cells are radially symmetric, and they do not have size or shape. Although you can define proxies to those, they do not have size and shape. They are point particles. You can also do a lot of impactful research. An example here is a tumor simulation implemented using PhysiCell. You can also represent cells as polygons. In this case, you're using a Vertex model. Oh, I forgot to mention before I jump here. The point particle approach follows Newtonian mechanics. So you can talk about momentum, conservation of momentum, mass, conservation of energy, these kinds of concepts. And in the vertex model, you can also talk about Newtonian mechanics, but now because your cell is a polygon, these forces apply to a vertex, to an individual vertex. And then you can pull and push these vertices, and they define the perimeter of the cell. I like wound healing models with Vertex model because they showcase the best application of Vertex models, let's say. Vertex models, they are very good for situations where the cells deform in response to force. And in a wound healing experiment or wound healing simulation, the cells are moving and they pull on other cells until the wound closes. And you assume that the tissue is confluent, so you don't have space between the cells except for the wound. So Vertex model is very suitable here. So we have these different implementations. And finally, the one that CompuCell implements, Cellular Potts Model. So CPM is the acronym. I'm going to use CPM from now on. Also known as Glazier-Graner or Granet in French, Hogeweg, GGH. In this implementation, the cells are a collection of pixels, and it's also a lattice based approach. So here your cell can have size because it's a collection of pixels. The size is discrete. In the case of vertex model, for example, the size is a continuous variable. Here it's a discrete variable. And it also has a shape as opposed to as a shape that you can vary as opposed to cellular automata. An example, and we will visit this example later today to practice using Player and Twedit, is the cell sorting simulation. I think it's one of the most beautiful and simple cases or applications of Cellular Potts Model. You can see that the cells are have these rough edges, the pixels that define them. They can have all sorts of different shapes and different sizes. Now, what governs the temporal evolution of like cell size, cell shape, and cell position in each of these implementations? In the case of cellular automata, the cells basically get deleted from a pixel and recreated on another pixel. That's how the cells move. And they cannot change shape or size. They are always um, the same kind of pixel, either a square pixel or a hexagon. Right? In the case of center models, what governs the cell position is Newtonian mechanics. So you have a potential interaction between particles. You can also define a self-propulsive or self-propulsion force. And the cells will respond to these forces following Newtonian mechanics or following Langevin mechanics. cells cannot change shape or size, although they do change their average distance to neighboring cells, and you can use that as a proxy to cell size. But they are always point particles, so zero size, and you cannot talk about shape. In the case of a vertex model, it's the same thing, but Newtonian or Langevin mechanics applies to the vertices instead of to the whole cell. And here the cells can grow in size, change shape, stretch, pull, and push. Finally, in Cellular Potts Model, the cells move by overriding other pixels with their own pixels, or by getting their pixels overwritten by pixels from other cells. And we are going to touch on next topic is what determines when a cell copies a pixel and what pixel it copies to, what pixels are allowed to overwrite. All right, so here the cells can, of course, increase in size, decrease in size, change shape. They can also, although you cannot really talk about Newtonian mechanics concepts such as mass, momentum, and energy, you can draw some analogies. For example, if a cell is overriding other cells' pixels, there is a force. You can abstract that. Well, there is a force happening here, and then the other cell will respond to this force by, for example, copying their own pixels in another direction and changing their shape. So they can squeeze, they can change their shape, change their size based on something that is happening elsewhere. All right, so what governs these pixel copies is an energy minimization strategy. And to understand exactly how energy minimization controls these pixel copies, we have to understand first what energy minimization is. So this is widely popular nowadays because of machine learning, but just as a visual example, imagine there is a gravitational potential and we have all these particles descending downhill. They are trying to minimize the potential energy by descending the gradient. So by going downhill, descending the gradient means they are moving towards the slope going down. Are intercellular processes taken into account in CPM simulation, or is it just cell scale? Yes, you can build a model where intercellular processes influence everything. Yes, we will do that later. Let's take this concept to the lattice, and because jumping right into the CompuCell algorithm using cells can be a little bit scary. This is a very accessible example to get familiar with how energy minimization can work in a lattice. So this is a little game. You answer two questions about this little game, and I'm going to read the rules for you. So we have a lattice. Each pixel has a value. This value represents an energy value. And we have Bob, our scientist. It is sitting over here in this pixel with value 15. So 15 is the energy of Bob in this pixel. If it moves to another pixel, it requires the energy of this other pixel. So for example, if Bob moves up, it has now energy 10 instead of 15. Back to the example. Bob is going to follow a set of rules. So Bob will first randomly pick a pixel, up, down, left, or right. And then Bob will ask himself, okay, is the energy of this other pixel lower than mine, than my current energy? If the answer to this question is yes, it accepts the new energy and steps to that pixel. If the energy in that pixel is higher, Bob will not go to that pixel. Bob will reject stepping towards that direction. If Bob keeps repeating this process over and over, what is the final position of Bob? 8, 7, 8, 7, or 10 if you allow diagonal jumps, either 8 or 7. Only right answers. Yes. It because Bob is picking random directions, it can fall either on 8 or 7. If you allow diagonal jumps, as Robert points out, you can eventually fall on -10. You cannot fall on -5 because it's surrounded by energy values that are higher than whatever energy Bob can have during his path. If he started with initial energy 30, it could go to -5. So can Bob reach the global minimum? The global minimum is -10. Can we get to the -10 if not considering diagonal jumps? You cannot. Even though the energy difference between like 10 and 11 is very small, you cannot because any energy increase is unfavorable. And this is often something we try to avoid. We try to not have these small energies um, prevent Bob from reaching our global minimum. This is just something that is not common, not natural. Imagine, for example, a stray cat or a street dog trying to find a cozy spot to sleep, to spend the night. And it finds like a spot that is cozy, a little bit warm, but not enough. It's still very, very cold. The best strategy is to keep trying to find another spot until it's warm enough. This is something you will often find, for example, when a cell is trying to find nutrients. It is in a spot where there is nutrient more than the surrounds, but not enough. This cell might move away and try to find another spot. Animals tend to do that. So giving allowance to Bob here to increase its energy might allow Bob to find the -10 spot, which is the best spot. So how can we change the rules of this game such that Bob has a chance of finding -10? We have to allow Bob to increase its energy. And then it might even find a -5, right? So if Bob has like an acceptance of increasing its energy or like a tolerance to energy increase, there is a chance Bob finds the -10. And it's impossible, this is impossible to happen if our tolerance is 0 to energy increase. And we have a question in the chat. How do you define this energy gradient in the first place? Is it physical? In the case of the balls descending downhill, the gradient is physical. The potential is called gravitational potential, and the force is called gravitational force. And the force itself is the gradient with a minus sign in front, is the gradient of the potential energy. So yes, it is physical. You define the gradient by using derivatives. More on that later on my other lectures 2 days from now. We'll talk about chemical fields and gradients of chemical fields. So to allow Bob to increase its energy, we need to give it like a tolerance function or like a probability that Bob will accept increasing its energy based on how much it tolerates. So there is a tolerance parameter. And also based on how much the energy is going to increase. Because if it increases too much, we might as well reject that. And if it increases just a little bit, we might accept it with a higher probability. So this is what this Boltzmann acceptance function does. If your energy is negative, so if your energy decreases, you have a 100% chance of accepting it. And if your energy is above zero, then you have a probability that is less than 1 of accepting this change. The higher the change in energy, the lower the probability that you accept increasing your energy. And the higher the tolerance parameter, the higher the probability that you accept this change. So in this video, you see what happens when you increase or decrease the tolerance parameter. As you increase, the probability that you accept an increase in energy is higher. And as you decrease the tolerance parameter, you have a lower probability of accepting the change. It follows this exponential curve. So the higher the variation of energy, the lower the chance that you accept. Any questions here before I move to how this looks like for a cell in a lattice? So we're getting closer and closer to what Cellular Potts model really does. How are we determining the tolerance parameter? On what basis? Awesome question. I cannot answer it right now because it's a very complicated answer. But that's one of the central challenges in all all of modeling. It's sometimes the parameters we set based on the behavior of our simulation. Sometimes there is a way that you can map this parameter to a real metric, something that you can translate to an experimental quantity. But usually it's very hard to say, oh, this is the tolerance parameter that I have to use. So usually what will happen during these lectures is you use the default parameter that we give, or you just set the parameter we are telling you to set, and then you play around that parameter. You see what happens if you multiply it by 10, you see what happens if you divide it by 10, and then you choose the suitable value of temperature based on the behavior you get. And this, maybe I already used the word temperature. I see temperature in the chat. Yes, this is the word I'm going to use for T from now on, temperature, because it's also the word we use in the code. This parameter is called temperature in the code for historical reasons. Okay, CompuCell3D comes from the original easing model, which is an actual physical model where temperature is temperature, the one you measure with a thermometer. However, in the biological models we are going to build, temperature is not the temperature you measure with a thermometer. Therefore, that's why I use the word tolerance, because it's more related to allowing the cells to fluctuate. So it's tolerance to fluctuation, tolerance to moving in a way that doesn't necessarily minimize energy, but it's not temperature in like Celsius, okay? Or Kelvin. I won't say the third one because I am international systems advocate. All right, let's keep going. So how does this look in a lattice where you have a cell? So if you have a cell in a lattice, Cellular Potts model comes into play. So now we are not talking more about the Bob example. Here we have a cell 1 is this set of pixels, these 8 pixels, 8 yellow pixels, and we have medium, all the other green pixels around. Okay? So to orchestrate the movement or how this cell move and change shape and change size, in space and in time, Cellular Potts Model follows these 6 steps. The first step is picking a random pixel of the lattice. We call it source pixel. Then it's going to pick a random neighbor pixel from the source pixel. We call this the neighbor pixel. Then it's going to attempt to convert the neighbor pixel to the source pixel. If the energy increases, you accept it for sure, 100% chance. And if the energy increases, there is an acceptance probability function, which is the same function we just saw. Let's follow these steps one by one. So first step, you pick a random lattice pixel. So in this example, I picked that pixel over there. That's my source pixel. Step 2, we pick a random neighbor pixel. In this example, my neighbor pixel is the one on the right. Then we are going to ask the neighbor pixel, do you want to become part of my own cell? Do you want to become the same thing as I am? And then we are going to ask our energy function, do you increase or decrease? But to ask this question, we have to define an energy function. So to start with, I'm going to use the volume of the cell to define an energy function, a very simple one. Okay? And my objective with this energy function is to constrain the size of the cell. I want the cell to have or to sustain a certain volume over time. Okay? So to constrain the volume of the cell, I am going to use a quadratic energy function. The quadratic energy makes the volume of the cell fluctuate around the target volume that I want. So if I set a target volume equals to 10, the volume of the cell will fluctuate around the value 10. And this quadratic energy is commonly used for constraining any kind of variable. So if you want to constrain volume, the cell holds its volume at a certain value. You use quadratic potential for that, quadratic energy for that. If you want to constrain the surface of the cell, you write the same quadratic energy, but for the surface. So it's surface minus the target surface squared. And if you want to constrain the elongation of the cell, so we call it length, the elongation of the cell, you can also use quadratic energy. This function has a minimum when your variable v volume is equal to the target. So when you set a target volume, for example, 9, if the volume of the cell is 9, that's the minimum energy configuration possible. And we multiply this quadratic term by lambda volume, or a lambda coefficient, a parameter of your simulation. And this sets the compressibility of the cell, the inverse compressibility, or the rigidity of the cell. So the higher your lambda parameter, the stiffer, or like the more rigid the cell will be. It will be like much closer to the target with much less fluctuations. So the takeaway here is the volume will try to the cell will try to keep its volume close to the target. And how close to the target it keeps is determined by the lambda parameter. So the higher the lambda parameter, the closer to the target, and the less the fluctuations around the target will have. So now I'm using my quadratic energy for the volume. So I have the volume of the cell minus the target. And I'm choosing 9 because 9 is a beautiful 3 by 3 square. Okay? So the target volume of my cell is 9, and the current volume of my cell is 8. Okay? So if my neighbor becomes part of the cell, does the energy increase or decrease? Decrease now. Okay, good. Good. So the energy decreases. This means we accept it. Okay? So this is the final state of the cell. We pick the source pixel, we pick the neighbor pixel. We ask the energy, do you decrease? The energy says, yes, I do. And then that neighbor pixel becomes part of the cell. So our cell goes from volume 8 to volume 9. Good. What if the target is 8? If the target is 8, then our question is increases. Our answer to the question, to the same question, is it increases. The energy is going to increase if a neighbor becomes part of the cell, if our target volume is 8, because our cell is already volume 8, is already at the minimum, and increasing its volume puts it away, further away from the target. So in this case, there is a chance it accepts that is defined by the Boltzmann probability. Okay, so Cellular Potts model will draw from the acceptance probability function, the Boltzmann probability equation. We'll draw from that, and you may or may not accept the copy attempt. Okay. This is again to allow fluctuation. You never see something sitting still and completely frozen. Sometimes you do, but in biology things tend to fluctuate. So this is a way in the way that CompuCell has to allow cells to fluctuate and move around. Otherwise, your cell will get stuck at volume 8 and never move, right? So you want some wiggle room for the volume of the cell. Again, so your acceptance function will depend on the amount of energy it increases by. In this case, the energy is going to increase by 1 because you have, sorry, in this case, the target is 9, so it doesn't increase. But in this case here, the energy of the cell is going to increase by 1. You have 9 minus 8, 1 squared is 1. And then multiplied by the lambda volume here, but our lambda volume in this example is 1. So depending on that, you may accept or reject a copy that increases energy. Okay, that's our first checkpoint of the lecture. What determines the value of lambda? What determines the value of lambda? So this is a similar question to how do we set temperature? How do we determine what is the value of temperature? And this is in practice, what happens is you are going to use a default value and you'll play around this value and see how the behavior of your simulation changes. Sometimes you can map this parameter to a real life quantity, something measurable in the experiment. So for example, if you have a cell in an experiment and you are like poking the cell and then you measure like the how much it deforms if you squeeze it, etc., and you extract a bunch of metrics, you can map that back to CompuCell and find what is the lambda volume that corresponds to the behavior of your real cell. This is possible to do. But usually in practice, you just set something that gives your cell the behavior you expect. What is a Monte Carlo step? You hear Monte Carlo step or MCS, and you read about it as well when you're studying about Cellular Potts model. So let's give it a definition. Monte Carlo step is our time unit, the time unit of our simulation. And what defines a Monte Carlo step is n pixel copy attempts, where n is the total number of lattice pixels. So your lattice has dimensions Lx, Ly, Lz, so it's a three-dimensional thing. And then the total number of pixels is the product of those three, Lx times Ly times Lz. And CPM will do n copy attempts, which might get accepted or rejected. After these n attempts, you finish one Monte Carlo step. That's one Monte Carlo step. And so you have your next state, the next simulation state after one Monte Carlo step, which is n pixel copy attempts. And a sequence of Monte Carlo steps is your simulation, is the time evolution of your simulation. And Monte Carlo steps do not have a connection to real life time units. Okay, so you cannot say 10 Monte Carlo steps is a minute by default. You have to define it. You have to come up with a map. You have to say, in my simulation, 100 times Monte Carlo steps is equivalent to an hour. You can also do this in a posterior way, like in a data analysis way, after your data analysis, using non-dimensionalization techniques, where you find the map between your Monte Carlo step and real life units, real life time units. So using non-dimensionalization, you can find what is the mapping in your simulation. Otherwise, you just set it. And there is a link here to what non-dimensionalization is in Wikipedia. And we'll also touch more on that later when we talk about cell division. Next, our final energy of the lecture is the contact energy. This is what is going to control the shape of our cell, or the edge behavior of our cell. Okay? So the contact energy has a scary formula, which I'm going to show in a bit, but the concept is extremely simple. So we have these two states, these two different states. The one on the left, we have our cell 1, which is the collection of all these yellow pixels, and these yellow pixels are disconnected. So they are spread around with a lot of contact with those green pixels. And on the right side, we have our cell 1 very compact with less contact with our green pixels. Question 1. If each edge between cell 1 and cell 2 counts as a +1 unit of energy, which one of those two is the most favorable configuration? And finally, question 2. If each edge between cell 1 and cell 2 counts as a -1, which one is it? The left one. So you guys got it. So this is very, very simple, right? This is the formula. So the formula is really like it's how you describe this mathematically, like this idea of like counting edges between objects of different types. Okay. The first term, we have a summation over I, j, these are pixels. I is all the pixels of the lattice, j is the neighbors of the pixels. And we are counting an energy thing. This is our contact energy. And on the right side, on the rightmost term, we have a summation over sigma. This is a summation over our cells, and we have the volume of a cell minus the target volume of that cell squared. This is our volume energy, okay? And this expression here, H equals all of this, is your total energy of the simulation, is given by this, if you have only these two contact energies. This is something that will show up in papers, will show up on Wikipedia, etc. I just want you to remember these very simple concepts. The concept of energy minimization via minimizing the edges, the contact between two objects, or via maximizing the contact with two objects. And the other concept of volume constraint, where the cell tends to keep its volume close to a target. Uh, the the +1 I was talking before, so I had this +1 or -1. This is our contact energy. We'll call it contact energy. It's a unit of energy per edge, okay, per contact. This is our J here. And J depends on what are the types of the cells you are considering. So you have a pair of types, A and B, and they come into contact. They have an associated contact energy J. So J depends on pairs of cell types. Okay? The value of J, which can be negative, can be positive, determines the affinity between these two cell types. If you set a very high J, you want to minimize contact so the cells have low affinity, they repel. If you set a very low J, low contact energy, the cells will try to stick together so they have high affinity, okay? I like the word affinity here. No. So the idea is for constraints where you want a variable to be close to a certain value, you use a quadratic formula. And the linear one for the edges is is linear. Because it's linear, you're trying to minimize it. If it's positive, you're trying to bring it to zero. But you could have a target contact energy. It would behave very differently. We don't have that. Um, we don't have that implemented yet. So the question was, is there a reason why energy is related to length, like contact energy is linear, and energy is related to areas is quadratic? No, the situation is because one is a constraint, so you want a variable close to a target, so you use quadratic for that. And a counter example is, for example, the length of something. You can set the length of a cell or the aspect ratio, which is something linear, and you also use a quadratic formula for that. Or the distance between two cells. You can also set a quadratic energy function for the distance between two cells, and this is also linear. So no, it's not because one is linear, the other one is volumetric or areatic that you set something quadratic. No, it's because it's a constraint. So let's say here you have different cell types in your simulation. You have cell type A, cell type B, cell type C. You have one J for each pair. So you have a J for A with a J for A with B, and a J for A with C. JAB equals JBA, so it's symmetrical. So you can build a matrix with only the top values above the diagonal. So you have the contact energy between cells of type A, between cells of type B, between cells of type C, and all the combinations, A with B, A with C, B and C. The takeaway here is if you set a larger contact energy, the cells will repel. If you set a low contact energy, the cells will stick together. Uh, so this is a breakdown of that ugly contact energy equation. First thing here, we have our J tau tau. Okay, tau is the type. I and J are pixels. So tau I is the type at the pixel I. Okay, we have the pixel I here, for example, and it belongs to a cell that has a type. That's our tau I. Tau J is the type of the pixel J. What is the pixel I and the pixel J? The pixel I is any pixel of the lattice. However, the pixel J is a pixel that is neighbor to the pixel I. Okay? So the first summation, we are summing over all pixels of the lattice. And then for each pixel of the lattice, we explore all its boundary. And we are going to sum J for each pair of I and J in the neighborhood. This summation will give us the contact energy. This term here, 1 minus delta, this delta is our Kronecker delta. It is 1 if the arguments are equal, and it's 0 otherwise. Sigma is the cell. The cell is an individual of the simulation. Okay? It's not a type. Inside a single type, you can have multiple cells, multiple individuals of that type. Sigma is the identity of the cell that the pixel I or J belongs to. Okay? So this is basically saying if the pixel I and J belong to the same cell, I'm not counting the contact energy because you have sigma I equals sigma j. This gives a Kronecker delta of 1. 1 minus 1 is 0, and then the contribution is 0. If you want to revisit this slide, feel free to do so, or ask me questions later. Okay? Unfortunately, we think it's not worth it to get everybody to understand all these symbols and all this formula, because really what we need is this understanding here. Okay? The maximizing or minimizing contact. One that might be important though is the range of interaction of our contact energy. So there is a parameter called the neighbor order parameter. It defines the size of interaction of the contact energy. So the larger this neighbor order parameter, the more long range this interaction is. So for example, if you set neighbor order 1 for each pixel I of that formula, it's going to explore a neighborhood that comprises only of up, down, left, and right pixels. If you set a neighbor order 2, you're going to get one, up, down, left, and right, but also the diagonals. So these are the second closest pixels to your central pixel. And as you increase your neighbor order parameter, you are getting a larger and larger neighborhood. So you have more and more contribution to your total contact energy as you increase your neighbor order. They look a little bit different depending on whether you're using a square lattice or a hexagonal lattice. But the idea that the first neighbor order is the first closest pixels, the second is the second closest, is the same. Oh, good question from Ajay. The pixel changes are accepted based on the contribution to the total energy that copy has. You could calculate the total energy after and the total energy before, but that's computationally expensive and unjustifiable. So what happens in CompuCell is you apply the copy and you calculate the energy contribution of that copy for each energy function you have in the simulation. And that contribution, you plug in the Boltzmann acceptance function, which is a delta E, a delta energy. So what you need is the delta energy. You don't need to calculate the total energy, just the contribution of that copy attempt you're trying to do. All right. Takeaway. This is how it's going to look like if you set a low J, an intermediate J, and a high J between two cell types. Sorry, yeah, between two cell types. So if you set a low J between cell type A and with itself, okay. Hayden in his cell sorting example will touch on multiple cell types. Here I'm just simplifying things and just talking about one single cell type. If you set a low J, your cells will pack and form this like dense layer of cells. And for an intermediate J, you'll have all sorts of behaviors. The cells don't really care if they are touching other cells or touching other things. And for an intermediate, for a high J, the cells will avoid each other. So there will be something else in between them to shield them from contact with other cells of the same type. So if you are like me and you don't understand things in the first time you're watching a lecture, this is the takeaway. This is the image that you should pay attention to. A low J, the cells will be very packed, and a high J, the cells will be very loose, scattered. In your code, you will find your parameters for volume, energy, and contact energy in the XML file. Okay, so there is one of those files of your simulation. One has an extension .xml. And you will find a plugin called volume, like this. Plugin name equals volume. And there you have the lambda volume, which is the number that multiplies the quadratic energy, and the target volume. which is the value which the current volume of the cell will fluctuate around. There will be another plugin called Contact, and in this plugin you have J's or contact energies for all the pairwise combinations of cell types you have in your simulation. So in this case, we have medium, medium is always there, and we have another cell type, cell. So we have contact energy medium, medium, medium cell, and cell cell. Okay. So for the next exercise, this is how you'll find your parameters because you're going to need to change them. There is an easier way to change the parameters, and you can change parameters on the fly as the simulation runs to see the immediate change in the behavior of your simulation as you are changing the parameter values, instead of having to close the simulation, changing the code, and then launching the simulation again, and trying to, like, you already forgot how your simulation was behaving before. Okay, so there is a way you can change the parameters on the fly, which leads me to the next slide, which doesn't start with that. It starts with play, step, pause, and stop. Okay, so these are the buttons you find on the upper left corner of your player. If you hit play, the simulation plays. If you hit step, the simulation will perform only one Monte Carlo step and then stop. Sorry, not stop, it will pause, waiting for you to give another step or press play or press stop. If you press pause, the simulation will pause and wait for you to run it again from the same from the same point, from the current point you paused. However, if you hit stop, the simulation will terminate, which means if you press play or step, it will relaunch the simulation and run from the beginning. So if you press stop, you are losing your current run. Okay? So if you want to just pause your simulation, do something, then come back and play it again, you are pausing and not stopping. Okay? Now in your player, there is small little page there called Model Editor. The Model Editor contains a table with all the simulation parameters you have set in your XML, which means from here you can access the parameter values for lambda volume, target volume, and all the contact energies. And you can change the values here, press enter, and hit play again. Your simulation will run with the updated parameters. Good question. Can you change the type of model? For example, let's say you have two implementations of contact energy. One is using a square exponent, an exponent 2. The other one is using like 1.5, or it's using like using just the norm of the difference in volume. Can you come here to the model editor and switch between the two? You can set it up. It's not something, it's not built in, it's not innate, but yes, you can set it up in Python. You can have two energy functions. You can set a parameter that says, for example, it could be like a string, like energy, type of energy one, type of energy two, and then you switch between the two on the fly. Yes, you can do that, but it requires a little bit of setup in Python. Do you have to use the GUI to change parameters? No, you can change the parameters in the editor and then relaunch the simulation. So you can go to your XML, like here, find your parameter values and change them there. All right, with that said, exercise one. In exercise one, I want you to achieve the first and second cell behaviors, where the first cell behavior is a cell that is roughly round and keeps its shape, keeps its size too. And the second one, I want something very similar. The cell is also keeping its size, but it has like a less round shape. It is more amorphous. So this is your exercise for now. Here are the steps. So you open Twedit if you don't have it open yet. You will create a new project, going to menu, CC3D project, and new CC3D project, and you will follow these steps. So you give it a valid name, hit next, 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 and then you add a cell type, just one cell type, and then you hit next and finish. And I will give you 5 minutes to follow these steps. All right, so I'm going to follow the steps myself. So I hope this works for everybody. So I have my slide instructions in the left side. And I'm going to very slowly follow them here. So I have my Twedit open. Let me just make sure this is version 4.9. Yes, it is. Then I'm gonna come to CC3D project, new CC3D project in the menu here. CC3D project, new CC3D project. Okay, I open this. And then I have this bad boy, the wizard. Okay. Simulation wizard. Here you give it a name. It cannot start with a number, okay? So this is not a valid name. So it has to be something like this. It cannot contain spaces. So it cannot be a new space simulation. It can be new underscore simulation. Or like this, new simulation. Then I hit next. Here I have my general simulation properties. And I'm going to hit next. Now I have my cell type specification. I have the cell type table with medium cell type. It's the default. And then I can add another cell type by clicking this field here, the cell type field. And then I'm going to call it cell. Or cell like this. This is not a name we usually recommend, cell, because there are other things we call cell. But for this first example, you can just call it cell and then you click add or you press enter. Yes, you can change the dimensions in the previous wizard page, yes. So if you want to change the wizard, the dimensions of the lattice, you come here and you set a different value for x. The first one is x dimension. The second one is y. The third one is z. If z is 1, you are in a two-dimensional lattice. If z is greater than 1, you are in a three-dimensional lattice. You cannot set them to 0. Okay, if you set one of them to 0, your simulation will crash. You cannot have a 0-sized pixel. Okay, so they have to be 1 or greater than 1. Okay. So I have here cell type, I give it a name, valid name, and then I press enter, and then it appears in the cell type table. In cell properties and behaviors, we are going to choose contact, and it should automatically select VolumeFlex. If it doesn't, you can check VolumeFlex as well. So these are the two plugins we're using. And then next. Ignore chemical fields, you just hit next. You can ignore contact and internal contact plugins. So just hit next. and then finish. Your simulation appears in the CC3D project panel on the left. If you double click it, by double clicking it, you open your XML and your steppables file, okay? We are just worrying about our XML, so I'm going to click here in the XML tab. And I can find my cell type. I have cell type, medium, and cell. I have my plugin volume here that has lambda volume 2 and target volume 50. And I have my contact energy. For each pair of cell type, I have a J cell type, contact energy. Then finally, I have my uniform initializer. So for this exercise, I want to make sure I have one single cell. So I just need to set the initial dimensions of my region to be the same width and length of my width. So the minimum x coordinate that creates my slab of cells, I'm going to set it to like, just as it is in the slide, to 10. The minimum y, I'm going to set it to 10. And then the maximum, I'm going to set it to 20 and to 20. And then the width, I'm going to set it to 10. And then I will hit Control S to save. Or you can also press one of these buttons here. The save all. If I hit Control S, it saves my changes. Now I can open player. You can open player by clicking this button here, Start CC3D. I usually like to right-click the simulation project name in the CC3D project panel. And then I hit this button here, Open in Player. So if I do this, player opens. This is a warning that I can ignore. Probably I am very zoomed in here for some reason, yeah. So this is my lattice, this is my cell in the corner, bottom left. And if I hit step, you see like there are a couple of changes on the cell if I hit step. If I hit play, then the cell moves around. So this is already our first case, right? So let me put this to the side. This is already our first case. Our cell is roughly maintaining its shape and size, okay? So if you achieve the first case, if you run the simulation, you already achieved the first case. Now, if I open here Contact, on the model editor, we have Contact, and I open all these drop downs here. I have various contact energies, which I can change and see how they affect the simulation on the fly. So to achieve the amorphous shape, one of the things I can do is try to increase the contact between the cell and medium, right? And one way of doing that is by decreasing the contact between cell and medium. So I will get this parameter here and decrease it. Let me decrease it to 1, and then I press enter. And you can see that the behavior of my cell changes. So now it is amorphous, like in the slide, okay? So if you decrease the contact energy, you are increasing the interface between the cell and medium, so your cell is less round. All right. Now, if I can do the third for you. So the third, if I set a -10, this is what happens with the cell. It's trying to maximize contact, so the cell becomes dust. And you can try the fourth. The fourth is basically your contact energy, you can set it to 0, and then you can set volume to like the lambda volume to very, very high. Then your cell freezes, and then you set your target volume to 1, and that's your cell, 1 pixel. Very stable. Eventually disappears. So I leave it 3 and 4 for you as homework, and then you can also try the advanced challenge, the porous and amorphous single cell, okay? Now our final exercise, so it's just 1 and 2 here, okay? For our final exercise, oh, the cell is faster now. I thought you were asking me to go faster, move faster, okay. These are the answers for the exercise in the slide if you want to double check. And for our final exercise, you switch to multi-cell. So I can stop the simulation here. Go to my Twedit. And now I can just change the initial cell layout as it is in the slide from 10 to 60 on the X coordinate and from 10 to 60 in the Y coordinate. But I want you to run, see what happens, and do what the slide is telling you to do. So you're going to change the contact energy until the cells fully separate. And then you are going to change the energy back down and see if the cells come back together or not. This is the final exercise. Yeah, good question from the chat. So does the contact energy include the edges between pixels that make up one single cell? No. Cell does not have contact energy with itself, just with other cells. It's 2:30, guys, so I'm going to show you quickly here the expected result. I'll come here to player and hit play. And this is the behavior. When I come here to contact, open these guys, and I change the energy between medium and cell to be something higher, like 30. Medium. Oh no, sorry. This one stays 10. Between cell and cell, if I change to 30, cell and cell, and hit enter, the cells separate. However, if I set it back to 10, they form clumps instead of reforming the original blob. Okay. And the reason why is because contact energy is a local interaction. It is not global. The cell here doesn't know about the cell here, so they cannot attract. They only attract if they come within reasonable distance within contact to each other. Okay, so this is the answer. Oh, how to open the window in the left, the model editor? You will go to View. There is a menu called View, and there is this thing here called Model Editor. If I unclick it, it disappears. See? So if I close it by mistake or something, I come here to View and then I check Model Editor. Then it shows here again. If we increase the neighbor order, the cluster becomes more circular? Yes. Is it because then each cell needs to have more neighbors if I increase the neighbor order? So as in my understanding, and I will have to draw it here, it's because an edge has a more penalty than something that is not an edge. So if you have a cell that is like this, and you set a neighbor order of 1, it's just seeing this neighbor and this neighbor. Okay, of course, this one and this one. Okay. However, if you set a neighbor order of 2, it's seeing this neighbor, and this neighbor. So there is more penalty for edges. That's why things become more round as you increase the neighbor order of the contact energy plugin. Oh yeah, good observation. If you let it run long enough, it becomes a blob again. Yeah. Yeah, maybe you can even prove that mathematically. For a finite region. Maybe it's something for just 2 dimensions. I think there is a theorem somewhere. Poincaré recursion. Yeah. There is a mathematical theorem talking about this. That if you are in like in a 2-dimensional thing, every particle come together, collide eventually, so you will always reform the blob if you wait long enough. But it's something like if you are in 3 dimensions or after, or for a dimension larger than something.
Ali, your question is actually relevant to the next exercise we'll do in Module 3. You'll get a chance to really look at how the contact energy values work. The short version is essentially there's an energy value for each type of interface between objects in your simulation.